Okay, so we are looking at moving out different objects. So we firstly talked about Newton's laws of motion way back about static and dynamic interactions. We're going to revisit this concept because these were some questions we didn't quite cover. So I like to use this opportunity to cover it there. If you look at your syllabus outcomes, we've actually covered through work done, kinetic and potential energy, and the other day we talked about power. So we looked at it in terms of rectilinear motion, we've looked at it in terms of force against gravity, and we've also looked at work done against air resistance and friction. So what we're going to look at is go through Newton's laws of motion, where you're trying to move a block or maybe two or three blocks, and what occurs in that kind of a situation and the role that friction might play. So if you look at this diagram here, we have block A and block B, and what's occurring is you apply a net force of 56 newtons. Some of you might recall this was one of the questions we covered in the quiz. I'll go through the do now later on, Sam. I'll just explain the concept here, and then we can go through do now later on at your own pace. So we have the net force of 56 newtons pushing the two objects in these two directions here. So what we know is, according to Newton's first law, if we have a net unbalanced force, then we would cause some type of motion. Now, if we have, and then we also know from Newton's second law, if we have a net unbalanced force, okay, we're going to cause some kind of acceleration in the system in the same direction that the force is moving in. Which means, now that I know what this force is, I can work out the acceleration for A and B. Because these two are connected to each other, so because these two are connected to each other, the acceleration in A will be the same as the acceleration on B. So that's Newton's second law, okay? And then Newton's third law states that the action force from A, so we have 56 newtons of force pushing on A. A will have some kind of force that pushes on B, and then B will have some kind of force pushing back onto A in reaction to this force here. Okay, so this is our Newton's third law in action between these two blocks. Okay, so how would I work out the acceleration of the system? Now, Newton's second law formula is force equals to mass times acceleration. Force is, in this case, 56 newtons. The mass is we are looking at the mass of A and B. The reason why we're looking at the mass of both of these objects is because they are attached to each other. So the fact that they're both attached to each other, we can add the two masses together. And from that, we should be able to find the acceleration that these two blocks will partake in when I'm applying this 56 newtons of force. Okay, and I found in the formula over here, the acceleration is going to be 4 meters per second squared to the right hand side. So that's the direction, or that's the acceleration of my two blocks. Okay? But we don't yet know what the net force that A is experiencing, and we don't know yet what the net force B is experiencing. And so that's the next sort of thing we can work out. Okay, so this bit kind of gives you a sense of that. So I know that the acceleration of the two blocks is 4 meters per second squared. Okay. A, if I want to work out the net force on A, F equals to ma the mass is 5, the acceleration is 4. So the total net force experienced by this box A will be 20 newtons to the right. Okay? If I want to work out the net force on block B, again using F equals to ma, 9 times 4, and I get an acceleration of 36 newtons, again towards the right. So that's the net force on A, and that's the net force on B. What you should find is these two forces should add up to 56 newtons. Okay? So the net force in A and the net force in B should add up to the overall applied force of my system, which is what I have here. Okay? The last little bit is to work out the force that an object is applying to each other. So let's say I have my block B here. I want to work out what force is B applying to A. Okay, so what force is B applying to A? And what's the force that A is applying back to B? Okay, so a very simple idea. We know that the net force on B is 36. We know the net force of A is 20. Okay, in order for block B to have a net force of 36 newtons moving towards the right, block A should also be pushing it 36 newtons towards the right. So the net force of B comes from the force being applied by block A. So block A is actually applying a 36 newtons of force, and so that's what we have here. The force that's being applied onto block A, so this bit here, is 56. Block A experiences 20 newtons, and it's applying 36 newtons onto B. So how does that work out, or how does that make any sense? Look at the net force in block A. Okay, so to calculate the net force of block A, it should be our applied force. So the applied force minus the opposite reaction force from B. So the force of B onto A. So now I've applied 56 newtons of force, and B is applying 36 newtons back onto A, which is 20 newtons of force. So this calculation we have here, using this idea of Newton's third law in this equation, that actually shows our previous calculation, 20 newtons, as correct. So there's that. Okay, so we're actually showing that the previous calculations is also correct. So that's what we are having here. Okay, other types of reactions of Newton's third law, if you have a look, is the normal force. So the normal force reacting to the surface it's on, and also the weight force pulling our box down. Also, if the box is moving, there will be friction force to counter across. We probably won't ask many questions related to friction, but in this PowerPoint slide, there is just one for you to consider. So these are some of the calculations we have here. I'll go through this little example here first. So you have two mass objects, A and B, and you accelerate them together on a frictionless surface. So we're assuming there's no friction here, okay? Now, then let's have a look what we have to play with. The first question says, what's the acceleration of the two masses? So what's the acceleration of my system? Well, A has a mass of 1.5, B has a mass of 3. So that's the mass there, that's our mass here. If I want to find the overall acceleration, okay, it's the applied force. The applied force in this case is 30 newtons. So if I substitute that, I'll find that the net acceleration is 6.67 meters per second squared. So these two blocks are being accelerated in this particular direction at 6.67 meters per second squared. If I want to find the force now exerted by B on A, so what's the force that this box is pushing back onto here? We already said it depends on the net force on B. So we need to look at that. So B has a mass of 3 kilograms and it's accelerating at 6.67 meters per second squared. So this is the net force it's experiencing, 20 newtons. Okay? In order for B to be having a net force of 20 newtons going this way, A must have pushed at it at 20 newtons. And we know that according to Newton's third law of motion, whatever force you're applying onto an object, you will experience an equal and opposite reaction force. So B will be pushing back on the 20 newtons, and so the answer is 20 newtons exerted by B onto A. If we have a look at a different scenario, so this time the 30 newtons is pushing this way across, okay? The easiest answer is to then just look at what A is experiencing. So the net force on A is 10 newtons. And like I said to you before, if it experiences 10 newtons going towards the left here, that means B would have been pushing it at 10 newtons to the left as well. Okay? Which means that the force that A is pushing onto B is 10 newtons. So it's just equaling the reaction force, or it's equaling the action force of B pushing onto it, and so that's the reaction force here. Okay, so there we have that. And so those are just some other calculation questions for you to have a go at during this time. And then we might come across a question where we are trying to work out the same scenarios, but with friction in mind. Okay, so let's say we have an applied force of 4,000 newtons, but we have a frictional force of 0.3 Newton per kilogram. Now this unit is actually acceleration. Okay, acceleration equals to force over mass. Newtons is your force, mass is your kilograms here. So this is actually the acceleration we're looking at. If I want to look at the net force applied to these two blocks, okay, it's the force you've applied to it minus the friction on the road. So the force we've applied is 4,000. The frictional force is the mass of object X and Y times our frictional force here. So we get this value here. So 3,000 plus 5,000, that's where the two masses are from, times 0.3, our acceleration. So the total net force applied by this truck pushing these two blocks across, the net friction, or the net force, sorry, is 1,600 newtons towards the right. Okay? Once I know what the net force is being applied on both these objects, combined, I can work out the acceleration of these objects as well. So go back to the same formula I used from the first scenario. The force that they are experiencing is 1,600, and then I just add the masses of the two objects together. And what I will find is the net acceleration is 0.2 meters per second. So 0.2 meters per second squared towards the right. Okay? So that's just for you to have a look at, and these are the answers for it. One of the questions I have here is one of the questions from an old independent paper from last year. As you can see, it's quite similar to the example we looked at just then. So have a go at completing this one and see if you can get the correct answer from there. Another example we're looking at is if we have a string on the object. So in this case, I have a piece of string that ties my Y box and my X box together. And I'm saying what tension or what force of the string is being applied between these two objects. Okay? And to put it simply, we have an applied force of 3,200 newtons. Okay? So our applied force is 3,200. We can also work out the net X as well. So maybe I'll skip to this next slide. And mind you, I will be posting this recording onto YouTube, or online, so then you can rewatch this explanation again. Okay, so first things first, you need to find the net acceleration. So this is what we have here. We have an applied force of 2,000 or 3,200 newtons. So this is our applied force here. We need to combine the two masses together. The reason being is because imagine if two objects are linked by a string and you're pulling on it, then essentially you are grabbing the two objects as if they were directly next to each other and dragging them along like so. So this is the same as this at the top here. Okay, so that's why we add the two masses together when there is a string attached to it. If you want to try and find the net force experienced by each individual box, X will be the mass times the net acceleration. That's the number I have here. And it has a net force of about 1,778 newtons towards the right. And for Fy, it has 1,422 newtons also to the right. Now, the tension on the rope, there's a couple of ways you can think about it. We can try and solve for this through mathematical algebra, which is what we did down here. Or you can just use a little basic knowledge or logic. So if you imagine you're trying to drag these two boxes, then you need this amount of force, okay? 2,000 or 3,200, okay? So that's the amount of force you need to move the two boxes. If I'm trying to look at the force of the rope, okay, this force, particularly this force here, the force I need on this rope is just enough to move this box here. Okay, so Fy. So Fy, in this case, would be equal to my tension force, because the tension here needs to be enough in order to move my little Y box over here. Okay, so that's why the tension force in the middle here would equal to this box here. If I want to try and solve for it as an algebraic equation, I'll just go through this here. Sam, I'll answer your question in a second. If I want to find the tension force, okay, it's the applied force, and let's use X as our reference point this time, okay? So the tension force here is our applied force minus the net force experienced by X, okay? Because these two are self-sufficient from the tension force. So 3,200 minus the net force of X, and you find that the tension force is the exact same as we predicted. It will be the same as the net force on Fy. Okay, and so these are just some practice questions on that as well. And then the very last one we're looking at is a mass on a string. And so how do we work out the acceleration of this moving block here? Okay, you can try and work it out in two ways. So you need to firstly work out the force due to gravity. Okay, so how fast is this object accelerating? So it's Fg we're looking at. We know that G is 9.8, but the next part we need to look at is the value for M. This goes back to the string. Okay, if you look at this string, like I said before, if the string connects two mass objects together, then essentially they're one mass entity. So the mass we're looking at is actually 10 plus 4. So the acceleration due to gravity, or the weight force experiences going down, is actually 10 plus the 4, and that's actually your weight force here. Okay? We don't have an example. And so once you do that, you'll find the weight force. Okay? And when you find the weight force of this going down, you'll know that the weight force of this, of G here, is the tension force dragging our box along. So maybe I'll just redraw that there. So our weight force is going down here. Because this block and this block are connected by a string, the tension force it experiences should be the same as the weight force pulling it down. Okay? So if we want to find the acceleration of this block here, we already know what the weight force is. So the weight force will equal to the net force on this particular block. So mass equals to acceleration. Okay? So the net force, 14 times 9.8 equals to our mass, which is 10 A. If you use your calculator, or you can do it in your mind as well if you want, the block we have here will be accelerating at 13.72 meters per second squared. So that's kind of a summary of what would be happening there. Let's just make sure I got that down correct. Okay, so that's how you sort of do that. I made one little error, sorry. Let me just fix that up. Okay, so one thing I did make the wrong assumption. So this bit here where we're calculating the weight force, it's just the mass of this object here, so our 4K. So it should be 4 times 9.8. I do apologize for that error. So 4 times 9.8, the total weight force is 39.2 newtons. Okay? What I said before, the tension that's experienced by our 10K mass here is from the weight force pulling this object down. Okay? So it still holds true that the tension force is equal to the weight force. So if I want to work out the acceleration of this 10 kg mass due to the tension force, F equals to ma. But because this mass is connected via string to this 4K mass here, that means that these two objects will experience the same acceleration as each other. So to write it more clearly, it should be 10 plus 4 here, and then times the acceleration that I'm looking for, and the weight force I'm looking at is 39.2. So it should be 39.2 over 14 equals to the acceleration. So the net acceleration experienced by both these objects is 2.8 meters per second squared. In this case, for the 10 meter or 10 kg block, it's going to the right. In the case of our 4 kg block, it is going down 2.8 meters per second squared. Okay, and so that's how you do that one. I'll just quickly go through, and those are the answers for question 8, and those are the answers for question 9. And then question 10, it asks you a scenario where you look into friction, and so I'll let you have a go at those ones as well later on.